In the vast expanse of the solar system, where sunlight fades into darkness and planets drift in silent majesty, there exists a small, icy wanderer, 2060 Chiron. Unlike the familiar planets whose presence has been etched into human consciousness for millennia, Chiron belongs to a class of bodies known as centaurs. These celestial hybrids drift between the outer planets, neither fully asteroid nor fully comet, navigating a chaotic path influenced by the gravitational pull of Saturn and Uranus. Chiron's orbit is erratic, a winding path that defies simple description, yet it is precisely this wandering nature that makes it fascinating. It is a world suspended between order and chaos, a reminder that the solar system is not a static clockwork, but a dynamic, ever-changing theater of motion and interaction. Discovered in 1977, Chiron initially confounded astronomers. Its size and orbit suggested it was an asteroid, yet on occasion, it exhibited activity more akin to a comet. It became the prototype for the Centaur class, bodies that challenge our neat categories, whispering that the universe rarely conforms to human expectations. But beyond its wandering orbit and occasional outbursts, Chiron held a secret that would astonish the astronomical community: rings. Rings, previously thought to be the domain of massive gas giants like Saturn and Jupiter, now encircle this modest 230-kilometer body. A small, icy fragment of the solar system, Chiron defies assumptions, revealing that complexity and elegance do not require immense mass. Even the most unassuming objects can harbor structures of breathtaking subtlety. The discovery of Chiron's rings did not come from dramatic imaging, nor from a spacecraft soaring through the outer solar system. It came from something far more delicate: the careful observation of stellar occultations. Astronomers positioned telescopes across continents to watch as Chiron passed in front of distant stars. For mere moments, the light from these stars dimmed, first in one tiny dip, then in a second, symmetrical dip. These signals were faint, fleeting, and nearly imperceptible, yet through careful analysis, a pattern emerged. Chiron was surrounded by two narrow, faint rings, circling in silent symmetry around the wandering world. This discovery challenged centuries of assumptions. Rings were thought to require immense gravity to maintain cohesion. Yet here was a body only 230 kilometers across, sustaining a structured ring system against the immense forces of space. Astronomers were stunned. What force, what subtle cosmic mechanics, could allow such a delicate structure to endure in the outer solar system? And perhaps more intriguingly, if Chiron could have rings, how many other small bodies might also host hidden, invisible adornments? Chiron's rings are composed primarily of ice, dust, and microscopic rock particles, delicately balanced by gravity. Their exact origin remains a mystery. Some hypothesize that they formed from collisions, debris from a shattered moon, or a cometary outburst cast into orbit, slowly organizing into coherent bands. Others suggest that the rings could be remnants of ancient ejections, material expelled by Chiron during periods of activity when sublimation of surface ices sent fragments into space. Unlike Saturn's grandiose rings, Chiron's are narrow and fragile. They exist on a knife edge of stability, susceptible to disruption over thousands or perhaps millions of years. Yet their very presence speaks to the resilience of natural processes. Even in the harsh, distant reaches of the solar system, intricate structures can emerge and persist. The study of Chiron's rings is not only about cataloging material composition. It is about understanding dynamics, evolution, and the interplay of forces that can sculpt order from chaos. Each particle in the ring, orbiting silently, tells a story of collisions, gravitational interactions, and the subtle balance of energy and motion. Chiron is not alone in the outer solar system. Another centaur, 10199 Chariklo, also hosts rings, discovered a few years earlier. Chariklo's rings share similarities with Chiron's in size and structure, hinting that rings around small bodies may be more common than once believed. Yet each system is unique. Chiron's rings are narrower, more fragile, and perhaps less stable than Chariklo's, reflecting the intricate interplay of size, mass, orbit, and past collisions. These discoveries have revolutionized our understanding of small body dynamics. They challenge us to consider that rings are not exclusive to planets, and that miniature ring systems may exist throughout the outer solar system, waiting to be detected by careful observation. Detecting rings around a tiny, distant object like Chiron is a feat of patience, precision, and collaboration. Astronomers rely on coordinated networks of telescopes spanning continents to capture the fleeting moments when Chiron passes in front of a star. Each occultation lasts only minutes, yet within those brief instants lies a wealth of information: ring width, particle density, and orbital characteristics. Even minor errors in timing or positioning can obscure the delicate signals. It is a testament to human ingenuity that we can detect structures invisible to direct imaging by reading the subtle dance of light across the cosmos. Chiron's rings remind us that science is not always about dramatic images or spectacular discoveries. Sometimes it is about quiet, meticulous observation, the careful extraction of truth from fleeting phenomena. In those small moments, we uncover secrets that would otherwise remain hidden in the darkness of space. How do rings form around such small bodies? The answer is complex and multifaceted. Gravitational interactions, collisions with smaller bodies, and cometary outgassing all play a role. One possibility is that Chiron once hosted a tiny moon, shattered by impact or tidal forces, its remnants forming a ring system. Another is that sublimation of ice during active periods ejected particles into orbit, which slowly organized into bands under Chiron's weak gravity. Unlike Saturn's rings, stabilized by shepherd moons and strong gravitational forces, Chiron's rings are ephemeral. They are a delicate equilibrium, maintained only as long as perturbations remain minimal. Yet this fragility is also their beauty. They are a living reminder that the universe is dynamic, where structures arise and fade, and even small bodies can display elegance before time and chaos reclaim them. Chiron's rings challenge our assumptions about size and significance. In a solar system dominated by giants, where Jupiter's storms rage and Saturn's rings gleam, it is easy to overlook the small, the faint, and the fragile. Yet here, a modest body of ice and rock achieves a level of structural sophistication once thought impossible for its scale. This invites a broader reflection. Complexity is not solely the province of the large. In nature, elegance often manifests in miniature, in places where we least expect it. Chiron teaches humility, patience, and the value of careful observation. Even a small, wandering object can host phenomena worthy of awe. Even in the darkness of the outer solar system, order can emerge from chaos. And in observing these patterns, we glimpse the underlying harmony of the cosmos, hidden in places invisible to the casual eye. The discovery of Chiron's rings opens new questions about the outer solar system. If rings can exist around centaurs, could they also surround other distant bodies, Kuiper belt objects, or small moons. Could this be a widespread phenomenon, previously undetected due to the subtlety of its signals? These findings force astronomers to reconsider formation and evolution models for small bodies. Collisions, outgassing, tidal forces, and gravitational interactions may sculpt rings more frequently than previously imagined. Chiron is no longer a lone curiosity. It is part of a growing tapestry of small bodies with hidden structures, hinting at processes that shaped the early solar system itself.